Okay, so now we move on to the energy systems. So the energy continuum shows us how the three different systems work together to provide energy for the resynthesis of ATP. They rarely work by themselves, they just work at different rates. And down here we have how long the other systems last. So the first one is ATP-PC, which lasts between 3 and 10 seconds. Then second, we have the lactic acid system, which lasts between 10 seconds and 3 minutes. And finally, we have the longest system, which is the aerobic one. This lasts for 3 minutes and above, and we'll go into further detail about that one now. Okay, so the aerobic system provides energy for the resynthesis process that is involved in adenosine diphosphate and adenosine triphosphate, and is comprised of 3 stages. The first one is aerobic glycolysis, followed by the Krebs cycle, and then finally into the electron transport chain. It works aerobically in the mitochondria and can last up to 90 minutes, and it uses fatty substances in our body and produces a yield of 38 ATP molecules. So the first stage is the aerobic glycolysis, which takes place in the sarcoplasm, and here we get our first 2 molecules of ATP. So first of all, our glycogen is broken down into glucose by an enzyme called glycogen phosphorylase. From here, the glucose is broken down into the 2 moles of ATP and what's called pyruvic acid, which is catalyzed by the molecule phosphofructokinase. Next, we have the pyruvic acid reacting with coenzyme A, which forms acetylcholine A. Then when the aerobic system runs out of glycogen, free fatty acids can also be used. For example, the enzyme lipase can break down fatty acids into acetylcholine A. And finally, fats can actually produce more energy than glycogen, but they require 15% more oxygen, making it less efficient. Next, we move on to the second stage of the aerobic system, which is the Krebs cycle. This also creates 2 ATP molecules and 3 other substances, as well as takes place in the mitochondria. So the acetylcholine we got from the aerobic glycolysis reacts with oxaloacetic acid to form citric acid, which is then oxidized and enters the Krebs cycle. From this cycle, we get 4 things. We get carbon dioxide, which is one of our byproducts. We get hydrogen, a yield of 2 ATP molecules, and more oxaloacetic acid, which is then reused to form more citric acid when reacting with acetylcholine A. Finally, we have the electron transport chain, which is the last stage of the aerobic system. It uses the hydrogen from the Krebs cycle to create more energy for ATP resynthesis. This stage takes place in the cristae of the mitochondria and produces a yield of 34 ATP molecules. So the hydrogen enters the last stage and bonds with 2 enzymes called NAD and FAD to produce NADH and FADH. NADH travels down the electron transport chain and produces ions and 30 ATP molecules. In addition to this, when FADH enters the electron transport chain, it produces another yield of 4 more molecules, and therefore we end up with 34 overall ATP molecules for resynthesis. So in relation to Mo Farah, during his long distance races, he would definitely be running for over 3 minutes, meaning he will be using the aerobic system and will be running at steady state exercise. So due to this, he wouldn't have the ability to use the ATP-PC system because it only lasts for up to 10 seconds, but he would not also be able to use the lactic acid system because that only lasts for up to 3 minutes. Therefore, the aerobic system would be perfect for him because it lasts for a much longer amount of time, and this would benefit Mo the most as he gets the biggest yield of 34 molecules, giving him a huge amount of constant energy. So finally, we move on to the neuromuscular responses. So we have what are called muscle spindles and Golgi tendons in our body. These provide sensory information about the intensity of the exercise we're doing. So here we have a diagram of a muscle spindle, and then here we have a Golgi tendon organ diagram. So due to the information we get about the steady state exercise, this allows for smooth and coordinated movement during steady state exercise. So a muscle spindle's function is to send a message to the CNS about the degree of a stretch when a muscle increases its pliability. From here, the CNS decides the amount of motor units required to contract the muscle to make the stretch smooth. Now the more the body is used to steady state exercise, the more efficient the muscle spindles are at transmitting this information. Therefore, in Mo Farah's case, it would be of a huge benefit because he's extremely used to running in steady state region. Now, Golgi tendons are sensitive to stretching activity and also the muscle attached to it. They send information to the CNS relating to the strength of the muscle contraction and then work with the opposite muscle spindle to create a very smooth and coordinated stretch during the state exercise. So again, in relation to Mo Farah, muscle spindles and Golgi tendons would work significantly well for an elite athlete like Mo. This is because as he works in steady state so often, his muscle spindles are very efficient at transmitting information about the degree of the stretch to the central nervous system. And because of this, the Golgi tendons will match this and work very well with the muscle spindles. So this would result in the contraction movement being very smooth when Mo is running in steady state region. So that is the end of my assignment. Thank you for watching.